Okay, guys, I'm going to do 3 examples. So this phase has to do with volume of solids of revolution. So all right, the formulas are exactly the same though. But when you've got a solid of revolution, which I'll describe what that is in a second, um, your cross section areas are either going to be, or your cross sections, your slices, are either going to be a disc or this thing that's called a washer. All right, so this would be a disc, and then a washer is like a donut looking thing. Okay, and then the disc just has, you know, a single radius, so its area is pi r squared. And this is all in your packet, guys. But a washer actually has 2 radii. It's got this inner one, which is like the empty space, which I'll call R1. And then it's got this longer radius that includes both the empty space and like the washer itself. And that length we will call R2. Not R squared, whoopsie, R2. And in a washer, the area is pi. Now inside here, instead of 1 radius, you've got 2, and you're going to subtract their squares. So it's going to be the big radius squared minus, I want to use lowercase r because I'm also using capital R for right. Okay, all right, so we'll do that. We'll do some examples using both of those. Okay, the region formed by the graph of G and the line y equals -6 is continuously rotated around the line y equals -6. So that's called our axis of revolution. All right. So like right now, this yellow part, that's the region formed by G and the y equals -6 line. Like right now, imagine it's flat, but then you take this and you just start spinning and spinning and spinning, and then the area is going to fill. So this yellow area, it's going to fill all of the space that it sweeps through. It's kind of easy to think of this as, you ever seen people with clay, you know, and they're making like a clay pot or something, and this is like spinning around and around and around. I don't know, that's kind of a nice visual. So this thing here, guys, it's not really like, it's not a container of any kind because all the cross sections are discs. There's no empty space. So this is just a solid, you know, block of something. Okay, we'll see ones that involve empty space. So, okay, rotate array. Forming a solid whose vertical cross sections are discs. So the vertical cross sections are discs. So we know we're going to be doing things in terms of x. A, find the area of the given cross section in terms of the appropriate variable, x in this case, because vertical cross sections. Use an integral to represent the volume of the solid generated when the shaded region is rotated around or about y equals -6. Okay, so part A. My area with respect to x, let me just write down the original formula, is pi r squared. Okay, let me focus this more. Okay, now we got to figure out how to get the radius is pi blank squared. Now look at your shape, guys. Look at the radius. It's right here. How could you find that length right there? You would do top and then bottom. You do top minus bottom. Top minus bottom. Okay, so let me fill that in. So a of x equals pi. What is the top? So the top is g. Everything's in terms of x, so that's g of x. Minus, the bottom is on the line y equals 6, so minus -6, or plus 6 right away you can do. All right, so here's the area. Is pi g of x plus 6 squared. Okay, part A. Part B, use an integral to represent the volume of the solid generated when this shaded region, this yellow shaded region, is rotated about this line. So guys, you just got to add up an infinite number of those disks. So for part B, you're just going to, I'll say V for volume. I didn't in the last video, but V equals the integral from what to what? These are x values, -1 to 4. And then you put the area inside, pi, g of x plus 6 squared dx. Okay, one example down. Second example. So the region formed by the graphs of B and F, here's B and F, so this is the region, the yellow region formed by them, is continuously rotated around the line x equals 5, forming a solid whose horizontal cross sections are washers. Find the area of the given cross section, then we're going to do the volume. Now guys, the difference between a disk and a washer is this. So this is called the axis of revolution. Whatever you're rotating around is called the axis of revolution. Here is our axis of revolution. And then the area, the region that we're rotating, there's no space between the region that is being rotated and the axis of revolution. There's no space between the yellow and this line. However, in this case, this is our axis of revolution, and there is space between our axis of revolution and the region that we are revolving. So if there's any space between the region that we're revolving and the axis of revolution, you're going to get like an empty space in the middle. So, and maybe it even helps like to look at it like this kind of. So just like imagine as this yellow thing sweeps through the air, it fills like all of the volume that it sweeps through. So imagine that. That would be kind of like a weird looking bowl. So this is kind of like a container. So basically, if it could be a container from revolving, you're going to have washers involved. If it can't be a container like this, there's no space in the middle for it to be a container, then you'd be using discs instead of washers. Okay, so yeah, every single cross section is going to be a washer. So guys, for part A, this is going to be A of y, all right, because we're doing right minus left because we've got horizontal cross sections. So A of y is going to equal pi radius 2 squared minus radius 1 squared, okay? Now, for both radius 2 and radius 1, so this is radius 1, and then radius 2 is this big long one. For both of them, you're going to use right minus left, okay? So I'll say that, okay, so I'll just say that this is right, and then I'll call that like left 1, and I'll call that left 2. You can call them both left and left, but I'll just, So radius 2 is going to be right minus left 2, that whole length. Radius 1 is going to be right minus left 1. That'll give us the empty space. Okay, and we're using right minus left for both of them. So I'll just go a little bit slow, guys, like for our notes. Use my phone. Pi. Okay, so right is 5 in both cases. So it's going to be 5 minus left 2 is the b function. So that's b of y, and then we square it. Okay. Oh, actually, I'm going faster than I wanted to. Okay, and then this is going to be minus, now radius 1 is the empty space. That's going to be right minus left 1. So again, 5 minus, and this time, this function is f. So f of y squared. Okay, now just for our notes, maybe I'll say, I'll be like right here. This is right minus left 1 squared. And then this is, no, it's not. It's left 2. Right minus left 2 squared, right minus left 1 squared. Okay, and you don't even need to label them the way I did. I just thought it would be easier to follow. Okay, so that's the area right there. Now for the volume, guys, you just have to add up an infinite number of these washers. So for part B, volume is the integral. Now these are y values. Lowest is -6, highest is 7, and then you just put this inside. Be very careful with your parentheses. There's a lot of them. Squared minus f of y squared dy. You need that dy at the end. Okay, now guys, this is a combination one. Okay, so same idea. We've got the region bounded by the graphs of R, C, and the line y equals -5. Okay, so the region bounded by those graphs is continuously rotated around the line y equals -5, forming a solid whose vertical cross sections are a combination of disks and washers. Find the area, find the volume. So yeah, guys, if you look at this, so here's the region that we're revolving. Here's the axis of rotation. From 0 up to 3, there is no space between the region and the axis. But then from 3 to 6, there is space between the region and the axis. So we're going to have disks here and then here washers. So if we were looking like this, like if this were a container, you know, you wouldn't be able to fill like anything down here that's just like part of the design. And then like starting here, you could fill, you know, that. Okay, so we're actually going to have 2 area formulas. So A, right, I'll say like disk. Area with respect to X, vertical lines. Okay, vertical lines, X. Horizontal lines, yeah, vertical cross sections, X, horizontal, Y. Okay, equals, this is just going to be pi r squared. Equals pi. Now guys, R for this right here, this R, this is the radius. You've got to do top minus bottom, top minus bottom. The top is -5 minus the bottom is the R function, and everything is in terms of X here, so R of X. Okay, so that's the area of the disk part. Now B, oh, no, that's not even B, it's still A. The washer part, pi R2 squared minus R1 squared, okay? So, yeah, so A of X equals pi. All right, guys, now for R2 squared, all right, R2 is the big radius. You could call it, it doesn't matter. It just needs to be big radius squared minus small radius squared. So let me, big, small. It's just got to be big and small. Okay, so the big radius from the center of the washer all the way to where the washer ends, top minus bottom. The top is -5. The bottom, again, is R. So this is going to be -5 minus R of X, okay? Minus, okay, so now we're going to have to square the small radius. Now for the small radius is the empty part. So for the small radius, still top minus bottom. The top is -5 again, but this time the bottom is C. The bottom is C. So -5 minus C of X. Okay, we're almost done, guys. Now for the volume, we have to put the disk section and the washer section together. So this is part B. So the volume is going to be the integral from, okay, so for the disk part, our leftmost x is 0, our rightmost x is 3, and then we put the area on the inside, and when there's this many parentheses, be very careful. dx, you need that dx there too, guys. Plus the integral from, so the washers start at 3 and then they go to 6. From 3 to 6, oh, I'll write small. And then this is pi. -5 minus r of x squared minus -5 minus c of x squared. Close, close, dx. Okay, so there it is, guys.